Alright, hello everybody. We're going to discuss in this video AC circuits. So an AC circuit has a power source, a voltage source that is going to depend on time, and we're going to assume that the dependence is like V naught cosine of omega t. So it has a peak value of V naught and it oscillates as a function cosine of omega t. This is the kind of potential difference that you will get when you connect something to an outlet. So the simplest circuit that we can analyze would be just putting a resistor or an inductor or a capacitor connected directly to the power source. So we're going to start by analyzing a capacitor connected directly to the power source. So this capacitor has a capacitance C, and we're looking at this moment when the current is flowing in the circuit in the direction indicated. The capacitor is getting charged by that current, and at that moment the sum of the potential differences along the circuit is going to be V naught cosine of omega t minus Q over C, which is the potential difference across the capacitor, and that is going to be equal to 0. So the simple solution that we get from this is that the charge in the capacitor as a function of time is simply the capacitance multiplied by V naught, the peak voltage, multiplied by the cosine of omega t. Very simple situation for the charge of the capacitor. The current in the circuit, however, needs a derivative. So we need to take the derivative of the charge of the capacitor with respect to time to get the current. The current is charging or discharging the capacitor. In this case, in the picture that we have there, at the moment we have a current charging the capacitor. The current is dq dt. So we take the derivative of our function charge, that gives us a minus sign, and the internal derivative of the argument of the cosine function is going to pop out an omega. So we end up with minus c v naught omega sine of omega t. Now to make things compare, to analyze the dependence on time of the current, it is more convenient to write the function minus sine of omega t in terms of the cosine omega t plus a phase angle. An angle, you know that the function minus sine of theta can be written as cosine of theta plus 90 degrees. So this is going to, writing it this way, is going to allow us to see how does the current, what does the behavior of the current, how does it compare to the behavior of the voltage that is applied to the capacitor. So from this equation we see clearly that the current is ahead of the capacitor by a phase difference of 90 degrees. So that means that the current in the capacitor, for example, is going to reach a maximum value before the capacitor voltage reaches a maximum value. So we say that the current in a capacitor is ahead of the voltage through the capacitor. The other thing that we see from this equation, if we write it in the form that you see there as 1 over omega c in the denominator, is that writing it this way, what's in parentheses looks like a resistance. So the term 1 over omega c is going to give us an idea of how what is the resistance that the capacitor is putting to the current flowing in the circuit. Okay, so as we said before, the capacitor current is 90 degrees ahead of the voltage through the capacitor, and another very useful tool to deal with AC circuits is to visualize the current and the voltages as vectors that are rotating with an angular frequency omega. The voltage and the current are all going to have a dependence of omega, and that dependence we can always write it as a cosine of omega t plus some phase difference. So all of these currents and voltages can be thought of as the projections on the x-axis of these rotating vectors. The technical name for these rotating vectors that represent currents or voltages is phasors. So the current phasor and the potential difference phasor in the capacitor have a 90-degree angle between them, and the current is ahead of the potential in the capacitor by 90 degrees. As I said, the x projection, the x component of those vectors, is the actual potential or current in the capacitor. So when you, if the potential phasor makes an angle of omega t, then its x component is going to be V naught C, that is the peak voltage in the capacitor, multiplied by cosine of omega t, that's going to be the voltage through the capacitor as a function of time, and the x component, the projection of the current phasor on the x-axis, is going to give us the current as a function of time. It's going to have some peak value, I naught, and as we said before, the current phasor is going to be 90 degrees ahead of the voltage phasor, so it's going to be I naught cosine of omega t plus 90 degrees. That's the angle that the current makes with the x-axis. So this is a very convenient way to represent currents and potential differences in AC circuits, so that's the one that we're going to use from now on. So again, I naught is the peak value of the current through the capacitor. From the equation that we saw before, we are defining this quantity that looks like a resistance. We're going to give it the letter X, X sub C, and we're going to call it the capacitor reactance. X sub C, the capacitor reactance, is defined as 1 over omega C. So the peak value of the current in the capacitor is equal to the peak value of the voltage divided by the capacitor reactance. The units for reactance are ohms. So one thing to keep in mind is that the equation current equals voltage divided by reactance only applies to the peak values. This equation should not be extended to the current as a function of time being always equal to the voltage as a function of time divided by the reactance. That is not true. As we know, the current as a function of time is a cosine plus 90 degrees function, whereas the voltage is just a cosine of omega t. So at any given time, the current is not going to be equal to the voltage divided by the reactance. The equation that we wrote before, I naught equals V naught over XC, only gives us or relates the peak values of the voltage and the peak value of the current. Now another thing to notice is that for a capacitor connected directly to an AC source, the capacitor reactance is 1 over omega C, right, as we wrote before. The peak current is going to be V naught divided by XC, which gives us omega C times V naught. So when we're dealing with a circuit that has a frequency, when the frequency of the applied voltage is very small, going to 0, these equations tell us that the peak current in the capacitor circuit is going to go to 0. The capacitor reactance goes to infinity, as the equation 1 over omega C tells us. So we can say that the capacitor is going to act like an open circuit with a effective resistance going to infinity at low frequencies. So the capacitor is like an open circuit. It's as if the capacitor had been removed from the circuit, leaving the wires connecting to it open, because that situation is a situation that we characterize with the infinite resistance. So the capacitor does not allow current to flow in the circuit when the angular frequency of the source goes to 0, when it's very small, at low frequencies. At low frequencies, capacitors act like open circuits. On the other hand, when the angular frequency goes to infinity, the equation 1 over omega C tells us that the capacitor reactance goes to 0, and the equation peak current equals omega C times V naught tells us that the peak current goes to infinity. So that tells us that at very high frequencies the capacitor is acting like an ideal wire. Remember that ideal wires have no resistance. The equivalent of the resistance of the capacitor in an AC circuit is the reactance, so the reactance is going to 0. So is an analogy, or we can say that the capacitor acts like an ideal wire at very high frequencies. It is basically as if the capacitor wasn't there, but we have just an ideal wire connecting that part of the circuit. Just to remind you, the symbol X that we're using here means reactance, and it represents the resistance of a circuit element when we place it in an AC circuit. The analog of a resistance, of the concept of resistance in a DC circuit, reactance is the analog of that for an AC circuit. Alright, let's consider another circuit element, an inductor, connected directly to an AC power source. So we'll see what the behavior for the circuit is going to be just with an inductor. So at this moment we have a current flowing in the direction indicated, and we're assuming that the current at this moment is increasing. The IDT is positive. So that tells me that the higher potential side of the inductor is going to be the upper side, and the lower is going to be the lower potential, the bottom of the inductor in this picture. So the sum of the voltages along the circuit is going to be equal to 0. So the applied voltage V0 cosine omega t and minus the difference in potential across the inductor moving in the direction clockwise, those two differences in potential should add up to 0, which tells us that L di dt should be equal to V0 cosine of omega t. So this equation is pretty simple to solve. We just have to integrate the right hand side with respect to time to get the current. So we can write that the current in the inductor in this situation is going to be V0 over L omega sine of omega t. One more time, we can write the sine of omega t as a cosine of omega t plus some difference in phase. In this case, since the function is sine of omega t, then we write it as cosine omega t minus 90 degrees. So in this case, when we have an inductor connected to the AC source, we have that the current in the inductor, we say that it's going to be behind the voltage in the inductor at any given moment. The current is going to be 90 degrees behind that. So current lags voltage for an inductor. As we did before, the number that is dividing the peak voltage, the analog of resistance, but in this case for an inductor in an AC circuit, we call that the reactance of the inductor, and the reactance of the inductor is defined as XL equals omega multiplied by L. So just to represent this with phasors, we have the voltage applied to the inductor. We're representing that as a vector pointing in some direction, and we know that the current lags the voltage by 90 degrees. So we can draw the current phasor as a vector making 90 degrees with VL, but behind it, since the direction in which these vectors are rotating is omega as indicated there, the current needs to be 90 degrees in the clockwise direction. That means the current lags the voltage for an inductor. Now notice that according to this dependence of the reactance of the inductor and the peak current, we see that when the frequency of the source goes to 0, is very low, then the inductor reactance is also very small, which gives us a current in the circuit that goes to infinity. So that tells us that at low frequencies, the inductor acts like an ideal cable. Basically, the inductor, it is basically a cable that has been wrapped around a core, and so when the angular frequency is very small, the Faraday law tells us that the inductor is not going to be generating a lot of induced potential along the terminals. So it's basically the inductor is acting just as an ideal cable would act in the circuit with a resistance equal to 0. If the inductor is the only element in the circuit, then that means that the current is going to be very large. So at low frequencies, an inductor acts like an ideal cable. The opposite end of this is when the frequency of the source is very high. So then our equations tells us that the reactance of the inductor goes to infinity and that the peak current goes to 0. So that allows us to conclude that an inductor behaves like an open part of the circuit. It's as if we had disconnected that part of the circuit, leaving a gap there, which we can characterize as an infinite resistance between the two wires, the two loose wires to which the inductor used to be connected. That's why we're saying that at high frequency the inductor behaves as if we had removed the inductor, leaving the wires open at that part of the circuit. That is the behavior of the inductor at high frequencies. It opposes the current flowing through the inductor with the current of resulting in a current of 0. For just a simple resistor connected to an AC power source, well, things are not very difficult. We know that according to Ohm's law, current is equal to the voltage divided by the resistance. So since we're applying a voltage to the resistor V0 cosine omega t, the current has the same dependence, cosine of omega t. So we say that the resistor current is in phase with its voltage. So if we draw this in a phasor diagram, we see that the two vectors need to be parallel to each other. The reactance, the resistor reactance, the ratio between peak voltage to peak current, is therefore just simply the resistance of the resistor. Alright, so this takes care of the basic how each one of these elements in a more complicated AC circuit behaves. In the next video I'm going to discuss what is the situation when we have these three elements, a resistor, an inductor, and a capacitor connected in series. Alright, that's it for now. See you next time.